talk about phase diagrams. So this is a phase diagram for water, and we have pressure on the vertical axis and temperature on the horizontal axis. And we have different regions. Here's solid and liquid and gas. And then we have different lines or curves. So this fusion curve represents where water changes from a solid to a liquid. There's a sublimation curve from solid to gas, and a vaporization curve from liquid to solid. There's a point at which all three of these meet, and that is the triple point. So at this triple point, the solid, the liquid, and the gas coexist. It's really weird. So we're looking at the state or the phase of the substance as a function of pressure and temperature. The regions tell us the conditions under which that particular state is stable. The lines or curves represent sets of temperatures and pressure where we have an equilibrium between the two states. And the triple point is where all three states are stable and in equilibrium. And so I've got a video here. T-butyl alcohol. And so they're pulling a vacuum on it, they're lowering the pressure, and it starts to boil. And they keep lowering the pressure and lowering the pressure. See over here? It's freezing. And it's boiling. It's boiling and freezing at the same time.
They can't make up its mind.
Isn't that crazy? Oh, it's just wild. There's some really weird things. Freezing and boiling at the same time. I know. It's really bright. Sorry. Anybody have any questions? It's kind of hard to know what to even say about that.
Could you move something when it's in that triple point, like or like the triple point like that? Could you move something through it, or would it be? Because I know it's freezing and boiling at the same time. Like, does it have the properties of more of a liquid, or is it just kind of
Well,
changing constantly?
it's not like a supercritical fluid where the gas and the liquid have merged into a single state. You do have all three states present. And so you could, move something through the gas or the liquid state, but the solid part is going to be solid. It's just crazy that they exist at the same time, set of conditions. Yeah.
But they're constantly changing at that point, like they're changing between.
Yeah, so you've essentially got an equilibrium because you've got things going from solid to liquid and liquid to solid and solid to
They're just
gas.
going all different.
It's all of it happening at the same time.
Chaos.
Yeah, it's mind-boggling in a way. So this is the phase diagram for water. Water has a fusion curve that has a negative slope. It slopes back this way a little bit, and that's really unusual. We can look at navigation through a phase diagram, and so you can look at, well, what if we stay at 1 atmosphere of pressure and we change the temperature? What's going to happen? Well, as we increase the temperature, we're going to go from a solid to a liquid, and if we keep increasing the temperature, we're going to get to a gas. If we do that at a lower pressure, though, way down here, we'll go from a solid directly to a gas and entirely skip the liquid part. You can also look at what if we keep the same temperature and change the pressure. Here, if we lower the pressure, then our liquid becomes a gas. And so what happened with that triple point is we're lowering the pressure, and we get to this point where all three of those exist. One of these weird things about water, it's not a good color. So if you take, say, you start at a particular temperature, oh, that's not in a good place. Over here. Normal pressure, and you increase the pressure on water. By increasing the pressure, you can cause it to melt. That's not how most things work. Most things, if you increase the pressure on a solid, it's just going to stay a solid. If you increase the pressure on a liquid, it may become a solid. But water is different. So here we have, this is iodine and carbon dioxide, and these have positive fusion curves. So if you apply pressure to a gas, you can cause it to become a liquid and then to become a solid. Water won't do that. This is carbon dioxide, and here, this is where 1 atmosphere is, and so there is no temperature at which liquid CO2 exists. You have to get up to at least 5.1 atmospheres of pressure before you can see liquid CO2.